My talk kind of tries to complement
So with that,
Ben's
are
talk
there any questions?
from yesterday, but I will not give you as much of a project update as I will give you a bit of a technical outlook. So welcome to my talk on GNU Radio Beyond 3.8. So as you can see, I've got 17 slides, of which I filled around 15 with actual content. I've got about 2 minutes per slide, a lot less if I actually want to put emphasis on the questions and answers that I hopefully have. So here we go. I'll very quickly introduce myself, then we'll have a short look back at what we achieved when we released 3.8, what we'll immediately do for the next release, and then we'll hopefully make Dan a bit happier and talk about what the next large version of radio brings. So let me get started with a really short intro on myself. I need to do that because I couldn't be here if some of these roles wouldn't allow me to do that. So my primary job is I work at university, try to reach for a PhD. I work in Germany at the Cultural Institute of Technology at the Communications Engineering Lab, where I mostly am doing exercises for a couple of courses. That's the probability theory for third semesters, communication theory 1 for the fourth semesters, and a few advanced courses, which have 40 students each about, kind of. And as you can see from the number of courses where I do the exercises, we are hiring. So if you're interested in, SDR, channel coding, whatever, I send an email to the mailing list that we're hiring. Just reply to me or reach out to me on that. I myself, I'm doing a PhD, as said. Mostly it'll be on low-density parity check systems on channels where the error probability is not constant. But as you can guess, I've not been doing that very much, so I've got to apologize to my professor there that I'm doing this stuff instead. Nevertheless, he lets me go, so here's my thanks for that. Other than that, I've earned a bit of money as a freelancing engineer. You might have noticed that I've helped run, not really run, a workshop with the Ethos folks yesterday. I'm still part of their support team, so I supply all the necessary grumpiness to Ethos support. And what's most probably interesting for you guys, I'm the technical maintainer of the GNU Radio project. So in that role, I've had the honor and honestly the joy of releasing 3.8 just a couple of weeks ago. And that was, on one hand, it was a big change. On the other, as you can see by the things that we've actually changed, that didn't address very much of the systemic structure of GNU Radio. What we did, we progressed our programming languages. So instead of being stuck with Python 2, you can now choose for the 3.8 release between Python 2 or 3. That's an XOR. You can use C++11. I very much encourage you to write beautiful C++. We ran an all-around source formatting. That was super helpful at getting, the source code into a state where it is actually a pleasure to work with. That wasn't the case before in very many places. We updated a lot of dependencies. We've updated our build structures. But to the end user, that mostly is under the hood. What the end user does see is that we overhauled GRC quite a bit. So you have seen from other presentations, and I do know that coming presentations will feature that too, that the GNU Radio Companion no longer has these boring straight lines, but these fun rounded curves. And this is interesting to all the academic folks. You can actually export vector graphics and put them into your papers. That is actually what you see on the surface. But that doesn't look like a big feature, right? That doesn't look like something that should have taken us 6 years to come to. So what did we do in the 6 years? Well, we had a lot of these under the hood, very pervasive changes. And back in the day, we decided that this should have been done on a separate thread, Git branch. That was the next branch. And the way we chose to develop that was that at some point we branched off the next branch, and all the cool new features, all the future-looking work, the dependency updates should happen on the next branch. And we had the main branch, which was the stable branch, where all the patches, the bug fixes happened to be on. And we had the master branch, into which the main branch was regularly merged, so to keep the bug fixes also available on the forward-looking, but not so revolutionary branch. But that actually led to stalling. Why? Well, if you had something that would only work with Python 3, or something that should require Qt5, or something that you simply didn't want to implement 2 times, you would do that on the next branch, right? But that next branch actually never saw like actual usage by non-core developers. So we had like a diverse a bifurcation in development, and that was not a good thing in terms of getting releases out. So turns out that you can stall development by being very progressive and having a very, aggressively forward-looking next branch. And we decided that we'll not do that anymore. So with the 3.8 release, we've decided that, okay, we've now set finally completely on the new development model where all features should go onto master, and basically bug fixes get happily backported to all the release branches, but please, please, please do work on this common master branch so that we don't, go different paths during development, because turns out merging 6 years of development is actually a lot of work. And now it's a good thing. As a maintainer, I was astonished by how much people were still willing to help get this out the door. Ben showed that slide yesterday where we compared last year's to current commit activity, contributor activity, and shows that if you promise to actually get this out the door, people will help you. So this is a big thank you for everyone that basically stuck with us through these longish periods of having no significant release. It wouldn't be possible if people hadn't been, okay, we're finally getting this done, and we're very motivated. One thing that I've also learned is that if you're doing something that is kind of a bigger release, you need to be extremely careful about how you word your release notes, because people will literally take a single word from that and say, okay, this is a minor release, which I meant with we're increasing the minor version number. And people were like, this is 6 years of work, that's a minor thing that we did. That was not perfect, but I think we've learned our lesson. We've got a lot of publicity from the release. I don't think that every future release will see the same, and I'll explain why I hope that's the case in a minute. Namely, what do we do now that we've got 3.8 out the door? Well, first of all, I need to talk to all the developers, and this is a very effective way of doing so, about how you will please develop in the future. This starts with the fact that master will become the coming ready release. So if you want something to happen to be in the next release, please develop it on master. That's kind of obvious, but it's not as obvious as you think, because if you want something to be fixed on 3.8, you'd be very tempted to fix it on main 3.8. So please do that. If you find a bug in 3.800, which is the current release, please do submit a bug fix. But if you can, please do that against master and tell us about this is a bug fix that applies to 3.8.2. We otherwise have to check manually whether that applies to and cherry pick forward or backwards. And if I can, I'd rather cherry pick backwards and backport stuff than trying to get something that was hard to fix on 3.8 into 3.9.2. That's usually the harder case. So that's all the magic. Work towards the future, not towards the past. I need to address a bit about the future of the 3.7 release series. I deliberately not put too much of that onto the slides because we're not able to make a hard guarantee that says, okay, we'll be supporting 3.7 for the next 20 years. Why? Because we had to release 3.8. We had to because our dependencies are dying. So if you're using 3.8, if you're using 3.7, then rest assured that if you find a bug, we will try our best to figure out what's wrong there, as long as it's not in a component that's been labeled deprecated for a long time. That's where most people find the same bug over and over again in. But I can't promise you that for example, Ubuntu 24.04 will still be able to run main 3.7 because that's literally not possible. So with that in mind, I think 3.8 has been a great success in terms of actually wrapping work up and getting into a kind of release regimen where we know how this all works. We now know how do we get contributions in, how do we get them in on time, how do we coordinate. Okay, if you do this bug fix by Wednesday, we'll make it into this next release. So this gives me a confidence that we'll be going much, much quicker towards 3.9. And that leads me to the opportunity to talk about 3.9. And if you've met me last GRCon and if you've met me at FOSDEM this year, you might have noticed that we kind of set on a few features already. So the first feature is kind of that will make the analog device guys in the room rather happy. We're upstreaming GRIIO. IIO is not an exclusive analog devices deal. It's the interface for basically sampling devices that analog is very heavily involved with. They support that with most of their devices, including the Pluto. But it's a standard thing to do. There's kernel modules for that, so if you've got like a zero-copy device, you might hook that up into the Linux kernel that way. It's an interesting platform, and that's why we're upstreaming it. We also upstream GRSOPI very much in the same sense. We want to make GNU Radio useful for as many people as possible, not only for the few that have an X310 sitting at home. That means that I don't think the situation where people had to go out, install GNU Radio, then had to install GROSMA SDR and RTL SDR and everything so that their $6 RTL dongle would work was a good situation. And I want to basically be a bit more like Python and come with all batteries included. So that's why we're also upstreaming GRSOPI. Just to be clear, we're not deprecating GRUHD. That's still a first-class citizen. So don't worry. Another feature that we do is we'll drop Python 2. That doesn't sound like a feature at first until you realize how much energy went into supporting both Python 2 and Python 3 in the 3.8 release. And we need to make kind of a trade-off between supporting everyone's use case and being able to still develop in a timely fashion. So that's why this, to me, as a developer, is a feature. And to me, as a user, is also a feature because I can now be sure that whatever I develop a GNU Radio program, the guy running it will run Python 3 and not Python 2.75, which is no fun to support. So with these promises made, do we wait another 6 years? I say we don't. We've been having internal discussions about that for quite a while now. And basically, I've settled on what I thought was an optimal schedule when I adopted the role of being the maintainer. And that is do 2 releases a year. They don't need to be large releases. Like I won't promise that 4.0 is out in a year. But we can now work towards like dedicated goals. We can say, you know what, on this day, 2020, that's the day when we stop merging any more code. That's the day when we start preparing actually like torballs, release binaries, this kind of things. And how that schedule would look like is, first of all, obviously I need to entertain the crowds. And since this is not Ancient Rome, I can't do that with gladiators. I do that with releases. So about a month before GRCon should be enough to keep you, entertained. That's the one release. The other release would be after FOSDEM, which is the free and open source developers meeting in Europe in Brussels, which would be about mid-March. Why then? Because that's an awesome opportunity to get like one half of the community into a room, talk to them, and coordinate work, and then get something done. This kind of dictates that the FOSDEM release would be often more of a janitorial release, where you do a lot of small stuff that finally needed to be done, and the GRCon release would, offer itself to being the one that you introduce cool new directions. But I guess we'll figure out how that pans out in the future by doing so. But that's basically the thing. About 6 months between releases. We are not setting up for saying, okay, this is going to be, we're always going to do a large major version release per year. We're setting targets. We're figuring out whether these targets can be done within a minor or within a major release, and then we decide upon that. All that we promise is that we're giving you definite dates on which you can expect your code to appear in the public as long as it works. 3.9 is fine and dandy. Comes with a few new features that we haven't written yet, so that's going to be a lot of fun. But what about the future? Like, where do we take GNU Radio? As Ben said, GNU Radio's gotten pretty old, actually. Like, it's 80 now. It can buy booze in Germany, yeah, it's not getting any less crafty with age. So how do we address the things that go wrong? What actually does go wrong? What do we need to address to, stay the top free software and, globally probably the most popular software-defined radio environment? And over the last GRCons, it's literally been the last 5, 6 GRCons that at least I witnessed, we identified a couple of things. The first thing is, well, our scheduling is actually pretty cool, but it's also pretty primitive. I'll go into detail on that in a second. We need to work on that because especially the embedded guys and the high rate people, they tend to want features that we can't offer with the current scheduling system. To do that, though, we need to learn a lot about how the system actually behaves, because as I'll explain in a second, this is actually not deterministic. The results should be deterministic, and whenever they are not, please file a bug. But the way things are computed is not deterministic at this point, and it probably never will for reasons. So let me talk about, for a second, how GNU Radio currently works. I think this is, for a lot of the attendants in this room, this might actually be an interesting thing to talk about. So what you see here is a GNU Radio Companion 3.7 flow graph. It's very minimal. It consists of 3 blocks. So what does GNU Radio actually do when you hit the run button? Well, you generate a Python file that tells GNU Radio, okay, I need to instantiate 3 blocks, and this is how I connect them. And then the flow graph starts. What does that mean? That means that GNU Radio checks the graph structure and figures out, okay, the only block that can actually do something with 0 input is the signal source, the source block on the very left. And it tells that, hey, you could now work. I've got 0 input samples on 0 input streams. This is awesome. And you've got half your output buffer in space, so please do something with that. And the signal source will go ahead, calculate a sine wave or cosine wave, fill the output buffer, half of the output buffer, like how much it's offered, with that data, and tell the runtime that, hey, I'm done now. I've produced 4,096 items. What now? That's the moment when the downstream block, in this case the multiply cons block, would get notified there's input, would start working on that input. In the meantime, remember, the signal source was only called with half the output space as possible output buffer. It can be called again, because there's still free space. It's being called again, so while the multiply cons is already running, the signal source starts running again, so we've now got a parallelism of 2 blocks running. The moment the multiply cons block, which should be rather fast compared to generating a cosine, is finished, the file sync is notified that there's now 4,096 items waiting for it. Now, that's usually not the case, but imagine the file source can't accept all 4,096 items at once. It can at most, say, process 1,000 of them at a time. So the file sync will then take these 1,000 items and process them, and at the end of its work function will return a value that tells the runtime that it only consumed 1,000 of the items, which is no problem because the runtime knows that this means the later 3,096 items are still unprocessed. So it combines these with the output of multiply consts that appeared in the meantime, which happens to be conveniently located directly after in memory. And we get like this kind of continuous flow where now 3 blocks can work in parallel, and there's no constraint on how many items someone has to consume as long as it's less than what's available or equal. That's awesome. That means we get high parallelism. That means we run blocks with the largest possible contiguous amount of input, which is very nice for throughput usually. And that's very convenient to program, right? We just spawn threads and tell the operating system that that thread, it can now continue. There's a notification message telling it that, hey, you're ready to work. With that being said, there's a few points that don't really fit well with us. So scheduler we always talk about the GNU array scheduler, and that might be a bit of a grandiose word for something that just informs the OS that you've got 20,000 threads and these 5 can now wake up. There's no exchange of data from the flow graph into the operating system, so there's no knowledge of who owns what data. So this is kind of like, if you think about that, that's kind of catastrophic. If you know anything about CPU, modern system architectures, and CPU and RAM, then you know that caching is very important for speed, because getting a single value from RAM usually depends on the CPU, something between 200 and 1,000 times the time it takes to multiply 2 numbers. So if you can, you keep stuff in cache. But migrating threads between CPU cores randomly because you just told your OS that this thread can now be scheduled again, and the OS just goes in and says, what CPU core is currently unoccupied, and then picks the random CPU core, executes that block on, instead of using the same CPU core that was computed to compute the input, used to compute the input of that block, leads to a lot of memory having to be flushed out to RAM and loaded into the other CPU cache. So this is very, very suboptimal, and we know that. The other thing, though, is this works surprisingly well. And it's been like, we are the most successful SDR framework, so it can't be so bad. And tests show that we can get better. So if you remember GRCon in San Diego, there was a company called Simple Executive, and Kirby Cartwright, I think, had a demo where they optimized a TV receiver flow graph, which is rather CPU intense, pretty drastically, like increasing throughput by, I think it was in the tens of percents, by simply pinning specific blocks to specific CPU cores, which eradicates the opportunity to migrate them between CPU cores. But there is like human intervention, and it's also not clear whether that was an optimal solution or whether they should have pinned more blocks to that thread, or whether pinning these blocks to the CPU core actually does what we want, because it might still mean that the block at the very end of the processing chain might be scheduled before, and we're again thrashing our caches. So with that in mind, we need to address all these issues in scheduling. Another thing that we need to address is that usually, like in digital communications, we are very much used to dealing with packages. We're not so much used to dealing with streams. Not everything is an FM receiver, right? So what we did in the past to come up with that, to deal with that, is come up with ways of tagging sample streams and basically emulating a packet interface on our stream-based interconnects. Those were the text stream blocks, and everyone who's worked with them probably noticed that they have some kinks to work out, and they might not be the greatest solution to that problem. So what I really envision here is that it should actually make no difference to a work function whether the buffer it's working on comes from a message or comes from a ring buffer, an emulated ring buffer as we do now with streams, or comes from, say, a GPU that is used as an accelerator. And also, there's no elegant way for a block that takes asynchronous messages in and outputs a stream of data, for example, to feed into an SDR transmitter, to go to sleep and with zero latency wake up as soon as there's a message. So ask Matt about that. I've had a very long and intense discussion over quite a few Club Mate at Congress or at camp. It's actually not trivial, nor it's not generally even possible. So we need to address that. I'm not going to go into too many details on this, but I think we need to talk about the next big thing, NBT. So what does that need to do? First of all, it needs to address the fact that CPU cores are not infinite, while blocks might very well be spawned in very large numbers. So we need at least an architecture that allows us to aggregate multiple blocks onto one CPU core and do that in a way that's kind of flexible. We need to have a single input queue per worker. I'll go into details on that in a second. And we need to be less dependent on where the data is actually coming from. So I'm now going into detail on these 3 points. That worker idea doesn't mean that we have to drop the mechanism that works so well at this time. The worker can still be a one-to-one mapping. And that's what you'd start with implementing, recreate what works well at this time. So ideally, we just re-implement the block executor worker to actually be less dependent on the exact way GNU is implemented right now and can more easily accept messages basically from anywhere. In the future, that you'd obviously aim for as many workers as you can actually deal with as you have CPU cores, maybe over-provision a bit if you know that not all of these will be working at the same time. Depends on your signal flow graph. If you've got these workers, then they need some way of organizing their work, right? And the way to do that, in my opinion, would be the single queue per worker. That there's a single queue of workload items that you want to deal with. That comes with a lot of advantages. Like from a programming point of view, you don't get a special blocked state that's different whether you're blocked on input space or blocked on output space. Your queue is empty, so you can't do anything. Or the top item in your blue queue is not able to be processed for some reason. That's the only thing that can actually work. If you've got a queue with items that are not yet being worked on, shifting these items to a different queue would actually be easy, right? Everyone knows how much of a pain it is to reconfigure a GNU radio flow graph in this time and age. It means that you stop all the flow graph, everything grinds to a halt, and then you restart and hope that all the hardware that you used in the meantime, retained its state. That can be pretty critical. Also, that queue could be clever. It could be assessing its own state. It could be able to, resort things if it turns out that maybe you can optimize cache access that way. The last thing is that a queue might just consist of workload items rather than making a distinction between messages to be processed and stream pointers to be advanced and then work to be called. You can just have a workload item that's like, okay, in this buffer, there's input items, input data like in a stream, or you might be, oh, this is a message, it contains input, please process that. We can work with the existing very successful semantics. We don't need to change what the GNU Radio block is, which is a very successful concept. It's a single class with a constructor and a work function, and that's what 99% of you usually care for. You implement the work function, it works. And you shouldn't have to care about whether your work function works on data from an OFDM framer or from an RTL dongle. So that's what I envision here. Also, that means that as soon as we stop caring about where that buffer space comes from, taking that buffer space and filling it with data from an RX queue on a network interface card becomes a lot easier. And we don't have to rely on the memory coming from some memory mapped emulated ring buffer. So acceleration is now possible. And he's telling me I've got 2 minutes left. So that necessitates a lot of changes. And luckily, these are pretty easy to categorize. That's benchmarking that needs to be done before and after. Obviously, we don't want to optimize something that works well, and we don't want to make it worse. We need to be sure that we're doing the right thing. And we need to refactor what is already in there. And so I'm very happy that Bastian has actually taken the lead on that. He's working on a branch himself in his very up-to-date radio repository. And there's already things being fed back into the mainline GNU Radio. And that is the immediate yield that we already have, is that some of the code in the scheduler is literally about 18 years old, and it doesn't work so great. And Basti has been refactoring that. Please do look over what he's doing. You'll find it on his GitHub. We now have benchmarking based on eBPF, so on Linux kernel facilities. That allows us to actually know when cache misses happen. That actually allows us to count how often threads were migrated between CPU cores. That actually allows us to look how long certain functions are. This is way more in-depth than control port used to do it for us. Also, and this is a nice side effect, it's way lower in overhead. So I think that's the logical evolvement of control port is, on perf counters is going this direction. Also, what Basti did is implement GRScat, which is a benchmarking tool that does test the current scheduler under certain. You can tweak the Linux kernel in ways that it schedules different processes differently. And we actually, Basti actually found out that not everything is optimal. That GNU Radio does, that Linux does by default. If you switch to the real-time scheduler, you can get pretty easy, pretty nice gains. So we might as well be doing that by default in the future. And he also says, okay, we're building a mock-up of an idealized scheduler that always employs the maximum cache coherency. And then we get graphs. Like, I very much like this graph because it looks so cool. That's basically telling us which block ran at a given time and how often it was migrated something. So you can't probably read it, but this is blocks in vertical and time in horizontal. There's a lot of interesting visualizations coming out of that, and I very much encourage you to check out GRScat because it is fun to run that, and it's far from being done. We need to incorporate information about how your hardware architecture actually looks like, and a way of reporting that back so that we can, in the future, actually do something about optimal scheduling for everyone instead of just for the developer's hexacore machine. So that's where we are. So what's the immediate things to do? We'll merge the refactoring and whatever we can immediately use for 3.9 as soon as possible, because honestly, that spaghetti code is no fun to work with. And we obviously change a lot of how GNU Radio works when we do the next big thing. And that probably will mean that we can't, keep the 3-point-something versioning, which I'm actually pretty excited about. So we'll see a generative 4 release that probably incorporates that. Not promising that it's actually going to be 4, it might be 5, because if something in between happens that needs us to change something, and I'm done. So, sorry.
Questions. Thank you, Marcus.
You'll find me.